Hello and welcome to another session of ENGR 330 Fluid Mechanics recitation on chapter 6. We already covered the first part of this chapter. Now in this recitation we're going to look at the second part of the chapter. So let's look at some problems from the recent material we covered in potential flows. So problem 650 from your book. As illustrated in the figure, a tornado can be approximated by a free vortex of strength capital gamma for r greater than rc, where rc is the radius of the core. Velocity measurements at point A and B indicate that VA is 125 feet per second and VB is 60 feet per second. You're asked to determine the distance from point A to the center of the tornado and also comment on why can the free vortex model not be used to approximate the tornado throughout the flow field, that is r greater than or equal to 0. So it's a free vortex, so we know that little v theta can be represented as k over r, where k is a constant, r is a radius. So we can define for point A, RA is the radius for point A. So the theta will be 125 feet per second, which we are given in the problem. So from here, using the above formula, we can get K to be 125 RA. Similarly, we can do this for point B and we can get K equals 60 RP. Okay. So the K is the same constant for the flow field. So we get a relation which says 125 RA is equal to 60 RB. Okay. And also we need another equation because we have two variables here. We know that the distance between point A and point B is 100 feet. So that would mean RB minus RA is 100 feet. Okay. So from here we can solve for RA. Okay. So I can solve for RA by writing entire equation in one variable. Okay, so 100 plus RA. So from here I get RA to be 92 feet. Okay, about 92 feet. In the second part of the question, you're asked the free vortex description cannot be applicable everywhere because you see that as R tends to 0, V theta tends to infinity. Okay, so the free vortex cannot be used to approximate throughout the flow field at r equal to 0. Therefore, free vortex at r equal to 0 does not apply. Okay, since the velocity becomes infinite. Okay, now let's look at another problem. If given a potential flow against a flat plate can be described with the stream function psi equals axy, where a is a constant. This type of flow is commonly called a stagnation point flow since it can be used to describe the flow in the vicinity of the stagnation point at O. By adding a source of strength M at O, stagnation point flow against a flat plate with a bump is obtained as shown in the figure. You're asked to determine the relationship between the bump height h, the constant A, and the source strength M. Okay? Alright, so we know the stream function for the plane flow or the flat plate flow. So we're adding a source. So we know that for a potential flow description, we can superimpose. So psi will be AXY plus the point source, which you can find in the book, which is m over 2 pi theta. Okay, and we can then convert the x and y coordinates into radial coordinates r theta, right? So I can write this as a r sine theta, and I'll put an r square cos theta plus m over 2 pi theta. And then I can rewrite this in terms of sine 2 theta. This will be a over 2 r square sine 2 theta. This helps us to do the differentiation easily if we have one function like sine here. Okay, so we have a stream function description for the flow. Now if you consider the bump, the stagnation point will occur at this point, right, at y equals h, right, and at this point, since this is the y-axis, your x value will be 0. And if you want to translate that to a theta and r, so r will be your h, and theta, if it is measured like this, will be your 90 degrees. Okay, so let me go ahead and write those. So stagnation point will occur at x equals 0, y equals h, or theta is pi over 2 and r equals h. And then for the given stream function, we can write the two velocity components, Vr, which is 1 over r dou psi dou theta, and which you do the differentiation, it will be ar cos 2 theta plus m over 2 pi r. And similarly, the theta component will be minus dou psi dou r, which is minus ar sine 2 theta. Okay, so now at this stagnation point where theta is pi over 2 and r equals h, Vr should be 0 and V theta should be 0 because the velocity itself is 0, so both the components should also be 0. Okay, so you see that automatically this equation satisfies that V theta is 0 because sine 180 automatically is 0. So if you substitute it in the Vr component, we get 0 equals a h cos 2 pi, which will be, it will be cos pi, that's just cos pi, plus m over 2 pi h, and cos pi is negative 1, so if you do the math and simplify it, you get h is square root of m over 2 pi a. So we could write our answer in terms of m a for solving h, the bump height h. Okay, now let's move on to next problem. A body having the general shape of a half body is placed in a stream of fluid. At a great distance upstream, the velocity is u, as shown in the figure. Show how a measurement of the differential pressure between the stagnation point and point A can be used to predict the free stream velocity u. Express the pressure differential in terms of u and fluid density. We are asked to neglect body forces and assume that the fluid is non-viscous and incompressible. So at this point, we know that we can go ahead and apply the Bernoulli equation, and for a potential flow we can apply it for any point any 2 points, right? So if I apply it from the Bernoulli equation, between the stagnation point, between the stagnation point and A, I obtain P stagnation is equal to PA, or the pressure at A, plus half rho VA square. Here we will have half rho V stagnation squared, but since it's stagnation point, velocity will be 0, that's why you ignore that term here. And now this VA term, if you look up your pages 308, 309 and 310, you can write VA square in terms of the U square. So let me write that. So I can write VA square as U square plus 1 plus 2 B over RA cos theta plus B square over R square, RA square. And you can look up what exactly are RA and B in those figures in those pages. And similarly, if you look up the analysis there, which will be equation 100 in chapter 6, R will be B times pi minus theta over sine theta. Okay, and then if you want to compute this at point A, your angle theta is 90 degrees. So RA, to be specific, will be pi B over 2. Okay, and since in your BA square terms you see B square over RA square, so let's try to write B over RA, which is 2 over pi. Okay, so that we can directly substitute this there. So then VA square will be U square plus 1 plus, you have cos 90, right? So cos 90 is 0. So it would be 1 plus 0 plus 4 over pi square, which is nothing but B square over RA square. Okay. So you substitute this, and then finally if you simplify it, you get pressure at the stagnation point minus pressure at point A. So this is the differential pressure, will be equal to 0.703 rho U square. Okay, which is in terms of rho and U square, which is what you're asked to solve in the as a final answer. Okay, let's now look at one last problem in this chapter. An ideal fluid flows past an infinitely long semicircular hump located along a plane boundary as shown in figure. Far from the hump, the velocity field is uniform and the pressure is P0. You're asked to determine expressions for the maximum and minimum values of pressure along the hump and indicate where these points are located. And express your answer in terms of rho, U and P0. If the solid surface is psi equals 0, a streamline, you're asked to determine the equation of the streamline passing through the point theta equals pi over 2, r equals 2a. So again, we have to look back on some of the analysis for flow over a cylinder on pages 313 and 314, and you will find the surface pressure on the hump, which is P surface, is P0 plus half rho U square times 1 minus 4 sine square theta. Okay, So now we have to determine when this surface pressure is maximum and also minimum. Okay, so the surface pressure is maximum when you have P naught plus half rho u square. That means sine theta should be 0, and sine theta will be 0 at theta equals 0 or 180, right? So max PS will be P naught plus half rho u square at theta equals 0 and theta equals pi. And similarly, the minimum pressure will be when sine theta is 1 or theta equals 90 on the top here, on the top of the hump, right? So will be, if you simplify it, it will be P naught minus 3 over 2 rho u square, which will happen at theta equals pi over 2. Okay, so these are the maximum and minimum pressures. And now we have to come up with the streamline passing through that point. So for a uniform flow, and remember we are talking about, if this is our positive x direction, our flow is this direction, so it will be in the negative x direction. So I have psi equals minus ur 1 minus a square, again you can find this on page 313, times sine theta. Okay, so now in this formula let's substitute theta equals pi over 2 and r equals 2a. So at theta equals pi over 2, r equals 2a, you get psi. If you substitute and simplify, psi equals negative 3 over 2 a u. And the equation of the streamline passing through this point would then be minus 3 over 2 a u equals minus ur 1 minus a square over r square sine theta. And you see that when you substitute r equals to a, theta equals pi over 2, both left and right hand side will be the same. And if you wanted, you can simplify this, but even if you leave it at this step, it would still be a valid equation. Okay, so this finishes the recitation on chapter 6. Looking forward to helping you solve more problems in the coming chapters. Till then, good luck.